What specific problem does the MindSearch method aim to solve in the context of information seeking and integration?
The MindSearch method aims to address the challenges associated with complex information seeking and integration tasks that traditional search engines and large language models, LLMs, struggle to handle effectively. Specifically, it targets three major issues: the need for in-depth analysis and proper decomposition of user queries before retrieving information, the overwhelming volume of web pages that complicates efficient information integration, and the limitations of LLMs in processing extensive search content due to maximum context length constraints. By employing a multi-agent framework consisting of a web planner and multiple web searchers, MindSearch enhances the reasoning and retrieval process, allowing for parallel problem-solving and efficient aggregation of relevant data. This approach not only improves the depth and breadth of responses, but also significantly reduces the cognitive workload compared to human experts, ultimately facilitating a more robust solution for AI-driven search engines.
Can you explain how the proposed MindSearch framework works? Please illustrate the process step by step, detailing the roles of the web planner and web searcher.
The MindSearch framework operates through a structured multi-agent approach, primarily involving two key components, the web planner and the web searcher. First, upon receiving a user query, the web planner decomposes the query into multiple atomic sub-questions, which can be addressed in parallel. This decomposition is modeled as a directed acyclic graph, DAG, where each node represents a specific web search task, allowing for a systematic exploration of the problem space. Next, the web planner dispatches these sub-questions to the respective web searchers, which are responsible for conducting hierarchical information retrieval from the Internet. Each web searcher generates refined queries based on the sub-questions, retrieves relevant data from various search engines, and summarizes the findings. This collaborative process enhances the efficiency of information aggregation, enabling MindSearch to handle complex queries more effectively than traditional methods. Finally, the web planner synthesizes the collected information to produce a comprehensive response, leveraging the structured context provided by the DAG to maintain coherence and relevance throughout the process.
Can you provide a simple example that illustrates the decomposition of a complex query by the web planner and how the web searcher retrieves and integrates the information?
An example of how the web planner decomposes a complex query can be illustrated with a user question like, "What are the environmental impacts of plastic waste on marine life?" The web planner first breaks this down into several atomic sub-questions, such as, "What types of plastic waste are most harmful to marine life?" and "How does plastic waste affect different marine species?" Each of these sub-questions is then assigned to a web searcher. The web searcher employs a hierarchical retrieval process, generating specific queries to search engines like Google or Bing, retrieving relevant web pages and summarizing the information. Finally, the web planner integrates the findings from the web searchers to construct a comprehensive response that addresses the original complex query, ensuring a thorough and well-rounded answer.
What advantages does the MindSearch framework offer compared to traditional retrieve-augmented generation, RAG methods, in terms of efficiency and accuracy?
The MindSearch framework offers significant advantages over traditional retrieve-augmented generation, RAG methods, by effectively addressing the complexities of information seeking and integration. Firstly, it employs a web planner that decomposes user queries into atomic sub-questions, allowing for parallel processing and more in-depth analysis, which traditional RAG methods often overlook. Secondly, MindSearch utilizes a hierarchical retrieval process through multiple web searchers, enhancing information aggregation efficiency and reducing the noise from massive web content, which is a common challenge in RAG approaches. Additionally, the integration of a directed acyclic graph, DAG for problem-solving, enables a more structured and efficient reasoning process, leading to improved response quality in terms of depth and breadth. Finally, the explicit role distribution among agents in MindSearch minimizes context computation, allowing for faster and more accurate responses compared to the more superficial engagement seen in traditional RAG methods.
How was the effectiveness of MindSearch validated? What experimental design was used? And what were the benchmarks or metrics for measuring performance?
The effectiveness of MindSearch was validated through extensive evaluations on both closed-set and open-set question-answering (QA) tasks, utilizing models such as GPT-4o and Intern LM2. 5-7B Chat. A total of 100 real-world human queries were curated, and responses from MindSearch were compared against those from Perplexity, AI and ChatGPT with a search plugin. Human experts manually selected preferred responses based on 3 key metrics: depth, breadth, and factuality, ensuring a comprehensive assessment of response quality. The results indicated a significant improvement in response depth and breadth for MindSearch, although factuality did not show the same level of enhancement. This experimental design, which included both subjective evaluations by human experts and quantitative comparisons against baseline models, effectively demonstrated the superior performance of MindSearch in integrating web information and reasoning capabilities.
What limitations or potential drawbacks did the authors identify in the MindSearch method, particularly regarding its handling of complex queries or information noise?
The authors identified several limitations in the MindSearch method, particularly concerning its handling of complex queries and information noise. Firstly, they noted that current LLMs struggle with decomposing complex questions and understanding their topological relationships, which can lead to coarse-grained search queries. Additionally, while MindSearch employs a hierarchical retrieval process to manage the overwhelming volume of web pages, the rapid proliferation of web content can exceed the maximum context length of LLMs, diminishing the effectiveness of information integration. Furthermore, the authors observed that the detailed search results might distract the model from focusing on the initial problem, potentially leading to hallucination issues during the web browsing process. Lastly, they acknowledged that despite improvements in response quality, MindSearch did not yield better performance in terms of factuality, indicating a need for further refinement in managing the context and ensuring accuracy.